5. Hopefully everyone hopes to make it. We're happy to jump into it. So before we jump into our presentation today, we'd love to do some intros. And by the way, we're really excited to be here. So thank you guys for coming. We're going to be leading our talk today on AI and how we're leveraging LLMs to turn AI into ROI. And how we help business take advantage of their data to improve the processes. So my name is Drew Whitney, and I lead business development here at 3 Sigma. And this is my colleague, Sergey.
Yeah. Hey guys, my name is Sergey. I am the CTO. I'm in charge of our product. And previously, my background was data science and research on Raponda. And part of the reason I'm so excited to give this talk today is just because back then we were playing with these early versions of these models, and just seeing how much the field has progressed has been, in the last couple of years, has just been awesome.
So going off that, if we dive a little bit deeper, but for the last 40 years, we've really largely relied on these extensive handcrafted algorithms, these rule-based systems to execute very specific tasks. And that takes time, right? And time has a cost. But now we're seeing a fundamental shift, a new paradigm in how we build these systems, driven by AI. So nowadays, rather than building these large systems by going through line by line, manually building and changing these systems, we're leveraging AI to do that process for us. And nowadays, we're training these AI models on vast data sets across a wide range of challenges to help us build these more flexible, adaptable systems for us. And with that, now our new models are becoming smarter, more adaptable, and more intelligent. But how do we get there, right? When Sergey and I were diving into this space, we saw the power that the industry is shifting and the power that these models are bringing to the way we're going to build things in the future. And with that, we started 3 Sigma, okay? So what is 3 Sigma today, right? Today, 3 Sigma, you may know of us from our consumer application. Currently, we have one of the leading chat with file or chat with document consumer apps, as well as one of the leading extensions on OpenAI's platform. And with that, we've had the power and the ability to ingest over millions of different documents, millions of different files, file types, and the real value here is that a broad spectrum of different topics have been filtered through our system. So we have data on file types from engineering documents to law documents, policy, contract revision, even textbooks people have uploaded into our system. And we've seen all these different types of files and began parsing through these files and provided over 1 million completions, customer guided or prompted queries on these data sets. And with that, we've been able to refine our model, hone in our algorithm, and now we recently launched an API to help customers take advantage of these lessons we've learned in our process to better their systems. Okay. How do we do that?
So what we want to talk to you guys about today is more the things that we wish we knew when we were getting started. So it's everything that you learn when you have tens of thousands of users being on your app that I think is missing from a lot of, conversations these days, where people are building these really cool POCs. But how do you take that into something that's in production, something that users rely on, depend on, and use daily? So that's really the heart of this talk, is just like some of the techniques that we've learned along the way.
And so going off that too, we have our consumer app, and we have 30,000 people feeding on this. We learn quickly, right? We have to learn quickly to be effective. And so to do that, we started leveraging these language models early on, and we've seen a great deal of growth and robustness in these models. And what we learned early on was that, yes, these LLMs are very, very powerful, right? But to really offer value and to offer value to our customers, we had to take advantage of not just these models that were pre-trained on whatever the data set was, but the real value comes when you can leverage these models to take advantage of customer data pertinent to your use case, specific to the problem you might be trying to address. And the problem that we saw back then was, how do we get this private data, maybe this data that's specific to a given customer and their specific use case, how do we get that into the model, right? That was the problem that we initially sought out to solve. And today we do that with a process called RAG. Right? Who in here has heard of the term RAG before? A lot of people. Okay, great. But for those who haven't heard of RAG, RAG stands for Retrieval Augmented Generation, and it's how we get the customer-specific data into these models to provide real value in their custom queries, okay? And for those who don't know what RAG is, we're gonna break that down for you today, and we're gonna dive deeper into really how we do this right now. But with retrieval augmented generation, it's really two parts. You have the retrieval side of it, which is how you get the different data, and then you have the generation side of it as well. So the generation side of it really comes from the large language models, and historically they've been pretty good about generating text, right? You can go on many different models out there today and ask it some questions, and it generates a text-based response. But oftentimes, if you ask it a question, if it's nothing too specific, it'll give you a pretty good response. But what if you want something that's date specific, or something that's more advanced, or maybe takes a little bit of background knowledge to know how to respond to that answer, right? That's where these LLMs today sometimes struggle in generating that optimal response. Sometimes it might be a little odd result that you're not really looking for, okay? And we've been improving on that process through RAG. And so let me just kind of give you an example of where the system really falls short today. So when I was a little kid growing up, I had a real passion for space. I loved learning about the atmosphere, the planets, and the moons. And back in the day, I used to study this and know all about it. So if you would have asked me back then, what planet in our solar system has the most moons? I would confidently tell you that I know this. I read an article once. Jupiter has the most moons. Okay, they have 88 moons. But there's a problem with that, right? I didn't cite my source, right? I just said I read an article at one point. And then with that, when did I read this article, right? Is it out of date? That's the same problem we see with large language models today, right? Where were they trained? What data set were they trained on? And when you ask it a question, where is that data coming from, okay? So if we go to a reputable source today, and we go and we search that same question, if we go to NASA and look for that question today, we'll find a different answer. Today, if you look to see what planet has the most moons, you'll see that actually Saturn has the most moons at 124 moons. And it turns out this number is actually changing because scientists are discovering new moons with the different technologies and different space probes going out into our solar system. But this LLM would have never known that. Just like I would have never known that because I haven't kept up on this data. And so the real problem that when we seek to really leverage these large language models in a specific use case is how do we give it the data that we really want to know about, right? And so that's where our retrieval augmented generation approach comes in. And that's where we develop something called a content store. So we can build out a content store on any given system. And that's the spot where we store all relevant data for our interested customer or any interesting situation. We add data in this that could be open. We can connect it to an online data source, a web page, an archive, a different data set, or we can lock it down and make it private. And we can upload fixed data sets to that as well, like such as PDFs and such like that. And then when we go through that same problem and want to know what planet in our solar system has the most moons, we still ask that large language model, but rather than just spitting out the answer that it thinks is right based on its training, now we reference that content store. So this is where the retrieval approach comes in. So now that large language model is going into our content store and looking for all relevant information. We're looking for what planets are out there, the moons, which planet has the most moons, and now we can generate a response that says, oh, Saturn has the most moons with 124 moons, right? So that's how we're implementing this retrieval augmented generation approach to start to leverage customer specific data. If you got questions, please take notes. We'd love to address them in the end. But so that's how we're taking this approach to leverage these large language models to add data to these models and keep it private as well. And what we're doing here at 3 Sigma is we're attacking it from both ends. From the retrieval side, right, optimizing the process in which we dive into this content store to look for relevant information. And on the generation side of it as well, how do we generate the best response for our users? And so to dive into the subject a little deeper, I'm going to pass on the presentation now to Sergey.
Yeah, so, and just to add on to what Drew was talking about, there's 2 fundamental ways that you can supply context to a large language model. And the one we're talking about is RAG. The other one is fine tuning. And I get a lot of questions like, well, why would I want to do this as opposed to like just fine tune a model? And it's kind of what Drew was talking about, where we have the advantage of being able to easily update the data set. And whenever you fine tune a model, you run this risk of OpenAI, Google, whoever, just releasing a better model tomorrow and it outperforms all the tasks that you've been doing. And not to mention, it becomes kind of this black box that you don't know how it's coming to its answer. So the agenda of what we're going to talk about, so there's 3 fundamental steps to RAG. We have parsing. So how do you get documents into that content store, which Drew was talking about? You have embeddings, which is how do we convert those documents into something that a computer can understand? And then finally, the fun part, retrieval. How do we get this back out? And then wrapping up, just future and then Q&A. So let's dive right into it. So the first step is parsing. So if you've built any sort of LLM application or you've just searched the internet, you'll probably come across a tutorial that basically tells you this is how you get data into that content store. And we're going to call it naive parsing. So in our example, we have a sample PDF document. What we're going to do is we're going to just use some sort of OCR to extract that text into just one giant, basically, text file. And then finally, we're going to split that text into n chunks. Why do we do that? Because embeddings are optimized to work on a certain number of chunks, and not to mention different parts of the document talk about different things. So we want to split that up. And this is great for getting started, and it's relatively simple to implement. But how do you preserve that semantic structure of the document, right? So when you and I look at a document, we look at it visually. So we see that this heading is right above this paragraph, or that this table has some subtext to it. And that is how we humans figure out how to get information out of like these documents. And when we take this first approach, we lose a lot of that information. And it's kind of like if I asked you a question and I just gave you a raw text file, you'd probably have a lot more trouble answering my question than if I had given you something really pretty to work with, where the information is well organized. So we can benefit through some of the breakthroughs in computer vision in the last decade. So we've spent billions of dollars tuning these models to basically figure out how to autonomously drive a car. And these models have gotten exceptionally good. So in this case, here's an example of what it comes out with. And these same techniques of spatial recognition, object delineation, are, if you think about it, the same techniques that we need when we're parsing the document. We want to figure out what goes together. So a visual approach preserves this data. There's machine learning models that now specialize in how do I extract the layout out of a document. And this is a far superior approach because everything is grouped together. So like I was mentioning earlier, a heading is right above a paragraph, and we can start to tie these things together as opposed to if I just chunk this document in random places. And the other really important part here is it becomes incredibly easy to display to the user how you came to your answer. And if you take nothing away other than this talk, from this talk, then that, you're probably going to be in a pretty good spot. This is absolutely crucial. So I'll actually give you guys a story. So before we did the consumer app, our first product was actually an email autoresponder. And what it would do, and this was last year before ChatGPT, before any of this came out, we would talk to people, they had no idea what AI was. And it would read through the email thread, and it would parse all these messages, and you could even type out what your response is. And then it'd spit out, in our opinion, like a pretty solid response. But when we started talking to customers, they're like, wow, like this is really cool. And I'm like really surprised to see that this is possible. But I don't know if I trust it. And to verify that, they need to go back through the email thread, back through everything, and double check that like, okay, this thing is like telling the truth. Because sometimes the reality of these models is it's not. And that's when we learned that it's so absolutely critical to show the user how you came to your answer. You don't want to just give them an answer, you want to show them the answer. It's kind of like if I ask you to answer something, one of my questions, and you refuse to show me your work, I'm probably gonna have a hard time trusting you. And this is the same concept. So 2, embeddings. So embeddings is something that you hear tossed around a lot. And I want to take a little bit of time to just explain what an embedding is to some of the people that might not be technical. So an embedding, on a high level, all we're doing is we're trying to represent a piece of text in a way that a computer can understand and compare. And how do we do that? It's through vectors. So this is a simplified version of this. We have 3 vectors, or 3 arrows pointing. We have a pineapple that represent 3 words: a pineapple, a cat, and a dog. And if you think about it, intuitively, a cat and a dog are kind of similar things, right? A pineapple is different. So the cat and the dog should be similar in vector space. The pineapple should be further away. And all an embedding is just quantifying that relationship in a way that we can then easily go back and compare this in a way that through a statistical method. So when you go to parse your document, you're going to see that off-the-shelf models are fairly powerful. Personally, we use OpenAI's Attitude. I think you can parse like 1 million tokens for under $1. Cost is incredibly low, and latency is also incredibly low. Then you have some of the open source models, which by a lot of benchmarks can actually outperform our proprietary models. And they're really powerful. They're really small too. You can run this on your laptop. You don't need some crazy supercomputer. And it's great for getting started. But they're not great for all use cases. So here's a warranty claim. And like I mentioned earlier, my background was previously doing data science at Compton. And what is a warranty claim? I want to take a step back here. So when you go into a dealership and you complain about a problem that maybe my AC is blowing hot, they fix that, and then the dealer will write down what the issue was when you came in. And then slowly that filters its way back into our systems. Now, this was a $500 million problem for us. It is such a massive expense, and we had a team of 40 analysts that were basically writing all sorts of crazy SQL queries to try to bucket these problems into distinct problem groups. So if a problem is not affecting very many people, we don't need to put the same resources into it as a problem that's affecting, let's say, 10% of our cars. And this is not a simple problem. But if you think back to that embedding example, this is exactly what embeddings are designed for. It's like, well, how do we group these similar claims together? And when we ran through this on just like a generic open source embedding model, what we found is that the results were pretty bad. Now, why is that? So let's read this. So faulty TPMS valve stem assembly leaking air. So what does that mean? So TPMS is tire pressure monitoring system. Valve stem assembly is a part of a tire. And unless you work in the car industry, and maybe even if you work in the car industry, you have no idea what this means. And then embedding models are no different. They are not tuned to prioritize these like super esoteric words. So if you're in an industry that has a lot of jargon, like so think engineering, think medicine, think in our case the auto industry, I really encourage you to look into these fine-tuned embeddings. And it's kind of an involved process, but it's getting easier. But this can drastically improve performance on domain-specific data. So if you have a lot of language that is very unique to what you do, this will help. And if we think back to that RAG, that search piece is so critical because it doesn't matter how powerful our models are. If we're giving them junk, they're going to give us back out junk. And we can't find something if the model, so the embedding models aren't picking up on it. So this is such a critical piece. So 3, retrieval. So this is the fun one. And there's been more PhDs than you can possibly imagine done on this. And there will probably be a lot more PhDs done. But at its most basic, all you're doing is you're searching for similar vectors that match a user's query, right? And let's draw that out. So here's an example of your typical RAG architecture. So you have your user query. How many moves does this have? You're going to feed that into an embedding model, which is going to generate that vector that we were talking about earlier. And then what you're going to do is you're going to compare that vector to all the other vectors that you have in your content store and you're gonna find the closest match or the closest couple matches. And you're gonna feed that back into a large language model, and you're gonna get back your final output. This is really powerful, once again, for getting started. But here's challenges that you'll start to run into if you start doing anything with this. So here's a great example of that. So we have our query. What is the total cost of a loan, right? And we have two elements that we're searching for. We have one that explicitly says the total cost of the loan is $120,000. And then we have another one that talks about the sum you'll ultimately pay back includes not just the principal, some legalese. And let's say that first option has a couple more sentences tacked onto it. And what you're gonna find, if you spend any time in space, is that sometimes a embedding model is going to prioritize that second option that we don't care as much about. And why is that? Embeddings do not care about keywords that much. What they're designed for is parsing the semantic understanding of that text. So what does the text really mean? And sometimes you're just gonna get back better. Sometimes it's gonna think that the information needs to answer the question is in something that happens to talk about the same thing, but not really. So how do we deal with this? So this is where traditional approaches can come to the rescue. So this is VM25, and it looks really intense, but it's been a cornerstone of information retrieval for a really long time. It powers Elasticsearch, it powers a whole bunch of the search technology we use. It's pretty fundamental. And what it does is it can actually excel at these keyword queries. And I'm gonna try to, it looks really intimidating, but I'm gonna try to break it down into its pieces. And then hopefully that'll give you an intuitive understanding as to why this would do a better job finding these keywords. So let's say I'm gonna search all of Wikipedia for what year was LeBron James born, right? So the first term here, all it's gonna do is it's gonna iterate across every single word in my query. So what year was LeBron James born? Then we're going to look at how often each word comes up in everything that we're searching. So think about the word year in that query. There's probably a million Wikipedia articles that mention the word year. So if we come across a match there, it's not going to be as valuable if we come across a match that says LeBron James, because a lot less Wikipedia articles have the word LeBron James. So all this is doing is just prioritizing that. Then this one is really simple too. You're just gonna adjust for the length of the document. So if you think about it, if you have all the same keywords of the same frequency in something that's one paragraph long, we should probably value that more than something that's 100 pages long. Because it probably has information we're looking for. And then the last piece of here, it's just some math magic to make sure that sometimes you'll get a match that has a really high score, and we just want to make sure that no one match overpowers everything else. So it's fairly simple when you think about it, and what it excels at is just finding, all it's looking at is basically word frequencies, and it's comparing that. As a result, these keyword queries, it can do a really good job picking up on. So this is where we get into this technique called hybrid search. So let's say we have our user's query. We're gonna run it through that same vector search we were talking about earlier. And then we're also gonna run it through a lexical search, which is the process we mentioned before. And it's really simple. All we do is just combine results and toss it to our LLM. And because of that, we get some stuff that is really relevant in terms of like core content, and then we get some good keyword matches. And this is a really powerful idea that will improve your systems, especially what we see is a lot of times people will kind of treat these apps like it's Google. And with embedding models, they just sometimes don't do as good of a job answering Google-like queries because that's searching keywords. But here's another one. Well, what if the user asks a broad question? So if you think back to our example, so here's a good, what is this document about? And the vast majority of documents will not have any specific paragraph that explicitly says this. So you're not gonna find any good matches, and you're basically gonna give the user a terrible response. So what we can do is in our parsing step, we parse this in, and then we generate a summary. And it's that simple. And then you're going to attach that summary when you query the document. And there's a couple different ways to attach that summary. But this is really powerful, especially when you get into this when you start searching a lot of different documents, this becomes even more important, because if I try to take a piece from here, from over there, from down there, and I don't give the model any context to what it's looking at, it's going to struggle to answer these questions. So this is a really powerful way of dealing with that. And this also goes back to this idea that we're so early in terms of LLMs, and like a lot of ideas here are actually like really simple. So how do we deal with this problem? I don't think this takes some rocket scientists to figure out. So yeah, that's kind of what's cool about space. But then, okay, you got back your results, but how do we figure out what results are most relevant? So now we're starting to like ask for a lot of different elements in our query, and some of those may or may not be relevant to what the person's asking for. And what you'll see, so here's another example. Can I have a pen in my apartment? We did our semantic search and we got back pets are permitted with an additional form. Fantastic. And then we had another one of these like legalese things. We follow regulations when we calculate the following costs. And if you show this to a user, the user is going to see that second option, and then they're going to be like, well, this has nothing to do with what I'm asking. And they're going to trust your system less because you're showing them information that is not pertinent to their question. So what we need to do is filter out the stuff that we got back from our search step that isn't helping us. And how do we do that? Well, there's actually ML models that specialize in this. And it's really powerful. Basically what they do is they figure out if a given question can be answered with a piece of text. But deploying this, it's a whole other thing we need to worry about. There's model drift, there's obviously all the complexity of running this model. What if you just use an LLM? And this also goes back to that central idea of why LLMs are so powerful. Because even though they weren't specifically trained on this task, they can generalize and they can actually do an exceptionally good job at doing this re-ranking step for us. So in our case, what we do is we use a fine-tuned version of GPT 3.5 that can re-rank our results. And we're basically just asking it like, hey, which of these results are going to help us answer a user's query? And it's going to drop the ones that are not relevant. And it does this with remarkable precision and fairly low latency. And then I'm actually going to throw this out here. If you're interested in the trained data set, go ahead, email me at SurveyFYI. I'd be glad to share it with you. But it's a really easy way to do this re-ranking. So yeah, these are low-hanging fruit that will improve our application. Most of the stuff is fairly simple to implement. I forgot to mention like a hybrid search, for example. It comes in just by default. All you have to do is enable it in a lot of these vector stores like Pinecone, VD8. Actually, I'm not sure about Pinecone. And with Postgres, you can do something similar. But these are fairly straightforward to implement. You don't need to spend a ridiculous amount of like engineering resources on this. Although some of these things do get more challenging. What I want to do is I want to talk about some of these more advanced techniques. And this is the part of a presentation that Drew and I are so excited about. Because how you get into the really cool workflows where you're truly augmenting people in just a game-changing way is when you start doing these more complex things. And this is where the models are going to, in our opinion, absolutely change what's possible. So here's an example. So some prompts can't be answered with one query. So we're going to see this. So here's our example. Compare the quarterly revenue for each division along with the average monthly expenses. And if you run this through your search step, what you're going to see most of the time is there's two topics here. So the quarterly revenue and the monthly expenses. And most of the time it's going to do a good job picking up on one or the other. It's not going to do both. And especially as these get more complex, you're just going to get back not very good results when you feed back in, and it's not going to lead to a good outcome. So what we do is this technique called query decomposition. And it's really simple. Another one of these things that looks really complicated, but we split this up into two subqueries. So in our case, the revenue generated by each division for each quarter. And then also monthly expenses incurred by each division. And by splitting this up into these subqueries, we can do a really good job finding results for each one of these. It's kind of like if I have an intern and they're helping me out with something, I find it helpful a lot of times to, like, if you break it into easy steps that they can follow, they're gonna have a lot easier time accomplishing a task than if you're working with just tell them whatever you want done. So this is, all it's doing is we're just splitting something really complex into simpler pieces that the model can understand. So we have our subqueries, we're gonna run it through a hybrid search, and then we feed that back into the AI model. And what you're gonna see is that it'll do an amazing job synthesizing this and coming up with an answer. And these are the areas where people will see your application and they'll be like, wow, like how did you do that? And this is like currently, like it literally takes a person to do this right now. In the next couple of years, this is we're gonna be able to automate so much of this and at the minimum just make people 10 times more productive. And this is kind of that central idea. These multi-step workflows will be able to automate more and more. And I think a part of this that's also really exciting to us is that most of the problems here are engineering problems. Like we don't need any the fundamental research. We have such an amazing base to work off. This is mostly just figuring out how do we use this in our specific systems. And that is just going to take us a couple of years. And how do we just make this reliably work? And this is all tractable. It's all doable. And there's already so much progress in the space on how you do these things. So the last thing I want to talk about is just the future. And this is a question we hear a lot of. It's like, okay, this is really cool, but I'm kind of curious where this is going. And we kind of have been talking about this like retrieval piece of this, how do you feed data into the LLM? But the other important piece is these foundational models. And the exciting thing about these foundational models is they're improving. And the way I like to break this down is there's 3, and as we improve these foundational models, we're gonna be able to do more and more and more. And it's gonna be awesome. But obviously, how do we do that? So there's 3 things. So 1, we can toss more compute at it. So on a performance per dollar, compute is going down. And more than ever, it's easy, it's becoming cheaper to deploy these massive superclusters that can train these models. So that's going down. We can use bigger models, which as we figure out some engineering of the GPUs and like all this other stuff, is also a tractable problem. Like, okay, even if we can do nothing else, we can just make the models bigger, and what you'll see is, for the most part, they'll tend to improve. And you literally see this from GPT-3 with like raw GPT-2, which I think had like 1 billion parameters, to now GPT-4 has like 1 trillion parameters. So in a couple of years, we went up a couple orders of magnitude. We'll see how far we can scale that, but at the same time, it's happening. And then the last piece of this is the most complex piece here, which is the better algorithms. So the core idea that's enabling all this is attention, specifically self-attention. And that was developed back in 2017. And we don't know when somebody's gonna figure out the next big breakthrough that helps us just do a better job architecting these apps. But I think what's awesome about the space right now is some of the smartest, most talented people in the world are just flooding into it. So personally, I'm pretty optimistic about this, that with the amount of people coming in, the amount of smart minds tackling this problem, we're gonna be able to figure this out too. And when we combine these, when we throw more compute at it, when we have bigger models and we figure out better algorithms, we're gonna get models that are vastly more performant than what we have now. And that's really something to be excited about. And I'll end the speech on this. So growing up, I always loved this girl. So Steve Jobs, he said the computer is like a bicycle for the mind. And what did he mean by that? He ran across a study when he was a kid that looked at the efficiency of different species per calorie, per kilogram, and just ranked them. And I think the number 1 was like elk or something. And then us crazy humans, we were like somewhere in the middle of the pack. So we actually didn't do a very good job. And somebody in the study had the foresight to also test a human on a bicycle. And the human on the bike drastically outperformed, we shot to first, by a huge margin. And what the central idea here is, it's like the bicycle takes us way past what we're innately capable of. And that's what he meant with the computer. And part of the reason I'm so excited about space is it really feels like pretty soon here, we're gonna be upgrading the motorcycle. So I'll hit on that, and we'll open up to Q&A.
Thank you guys. We can just go down the line, I guess. You first question?
Yeah, so awesome, really valuable. I was curious what your thoughts are on using like a maybe quote unquote like dumber, off the shelf, cheaper model versus RAG to feed in context. Because with what I'm building, I always run into the problem of just like token costs, which is the scalability problem. So I'm curious if you think that's an option now or will be in the future that would make sense over RAG.
So if I understand correctly, you're saying, so you're trying to, I'm trying to understand, so what you mean by that is that you're getting data in an application, like you're just prompting it, or do you need that like extra like content that it needs to be able to reference?
So I guess like for my specific use case, we're building like databases of information on company level for a large list of companies. And then based on certain prompts, it has to pull in contextual information from those databases, and sometimes they're pretty big. So RAG is something that we're doing now. However, I have just been curious, I'm like not as technical as my co-founder, but I have been curious, like, is it possible to use something that's like a lower cost model to just identify the relevant information versus using RAG?
Yeah, you could. And realistically, that's just gonna add some extra complexity, like a good amount of complexity to whatever you're building. In our opinion, most of the time, go for what's possible off the shelf. And then unless you have really stringent security requirements or you're parsing just insane amounts, I would probably stick with that. And the cheaper models, it's still, there's a lot that goes into running those. Yeah.
Sorry, I don't know if you were done.
Yeah.
The next question was just, I was curious about your slide that you had about the subqueries where you divided things into queries. Are you using a model to do that transformation there too? To actually like something say like, hey, can you split this up into independent tasks or something?
Yeah, and this is that really powerful idea of just chaining these things and then using the model on stuff that it wasn't explicitly trained on, but it can still do with exceptional accuracy. And as somebody that's worked in the space for quite a while, like before we had data science models for like each one of these steps. And now you just throw GPT-4 at it and it'll do a better job.
I have a specific question about embeddings that I don't quite understand.
Yeah.
So as I understand it, you get the words in the vector space. I get how all that goes. But when you're sort of taking your PDF and chunking it and embedding that, is it getting embedded as the phrase, or is it still individual words? Like I don't quite get what's getting embedded and how that gets pulled back. Like, is there a reference database that hooks to the words? Like,
so it's super simple. All you're gonna do is you're gonna link the text to the vector that is embedded. And then when you come across a match on the embedding, all you have to do is just pull in the text.
So it just ties those two.
Yeah, that's it.
I see.
Yeah.
Okay.
So like you can almost think about it.
So the vector space is individual words, but it's tied to that chunk that you popped it into.
Yeah.
I see. Okay. So it's a mapping thing.
Yeah.
Okay. Thank you.
Go ahead.
So you talked about the difference between vector search, lexical search, and then I've had a hard time trying to figure out how to add temporal elements to it. So let's say there's a correct answer, and the president
Going back
is,
in time. Yeah.
well, let's not do that one. XYZ is still alive in the future, they're not. The answer is right today, but it changes tomorrow, or if you asked it in the past, it would have been different.
Yeah.
How do you deal with temporal context, besides just passing in metadata?
Yeah, and just to kind of explain that idea to anybody that isn't familiar with it, it's like if I ask, hey, what did Sergey do before he started research? And it's like you need to find that like point in time when like this event occurred, and then you're gonna look backwards. And that's actually not a super simple problem. There's some techniques that you can do there, but I think there's a lot of active research going on and just like, what is the best way to do that? Yeah, it's not something I have a ton of experience with, but I've seen some projects that are really promising. And I would just, maybe start there.
You have to do that with process. It's like a steady state approximation where the data coming in is what's dictating how the information changes happen.
Interesting.
Earlier when you had the graph that had doing the vector search and the lexical search at the same time, I just wanted to clarify, is the lexical search that wild math problem you had a
Yeah.
couple slides back?
Yeah.
Okay.
There's a couple different ways, there's a couple of algorithms that specialize in that, but yeah, literally it's just doing like one of these traditional approaches that has been serving us really well for the last 30 years, and then adding it to what we're doing now. Kind of taking the best of both worlds, like we don't want to throw the baby out with the bathwater.
Thank you.
How are you verifying your data sets and make sure that they're clean and you're not getting, especially when you're pulling PDFs with OCR, you're gonna get errors and you're doing larger and larger data, you're gonna have more errors in it, so.
Yeah, so for the most part, OCR technology is like really powerful. And it does a remarkably good job with parsing text out of this. I'd almost consider this a solved problem. So there's like, I don't think it's, with the technology that's available right now, like it's such a small percentage of documents and files, like maybe if you're like trying to parse like newspapers from 1900, and even then.
Even something like a resume that you put into the systems, I'm seeing tons of errors where you can't figure out where your separations are on the lines and how it looks. I mean, if you put that into a data set and start training a model off of it, you're gonna, mess up your base.
Sometimes maybe the solution is just to use bigger chunks. So like for a resume as an example, it's like, well, instead of trying to parse it into specific parts of a resume, let's just throw an entire resume at it. Yeah, it'll work.
So we give it multiple so you're saying give it hundreds of resumes instead of giving it a few.
So basically, you're gonna come up with a vector that represents that resume. And then let's say you have 1,000 resumes, just compare the vectors. And then when it comes time to like toss that to the LLM, just throw the entire text of the resume at it. Like it's not gonna be about.
There's some models that are designed to read tables and like scientific documents. So trying to find something that does OCR on structured documents.
Facebook just released a paper, I think this week about this actually.
Yeah.
About trying to process papers from the 1900s and maintaining like the algorithms that they wrote and how they wrote it, and with handwriting and the syntax, and it's remarkable like how much it, because they're doing it for the historical preservation of these papers too, right?
Yeah, so and maybe that's something else you look into. There is like parsing math models that like specialize in these very niche use cases. That's a fantastic example, like old newspapers. But with something modern, I would almost like the amount of complexity it adds, I'm not sure you really need that, but you can try that.
Keeping your database up to date. I mean, we've talking about a bunch of corporate documents. Those change a lot. Right. So you have to re-index new ones, and potentially getting to the temporal issue, you want to fade out ones that say that so and so is still alive or whatever. Have you found a cool way to do that? I mean, I've done that with with user feedback. Basically, if you're giving feedback to the employees to help them do their job as an assistant, they will often know that person's not here anymore. You have a thumbs up, thumbs whatever. You just have something that says click, and you get enough down clicks on some source. You're like, let's get rid of this. But I wonder if there's a better way to kind of do that.
So, and what I think you're describing is like honestly an amazing approach, and something that's so important to keep in mind here is that we want to enable our users to somehow give feedback on the system. So in our case, on our consumer app, all we do is just like, do you like the completion, do you not like it? In your case, like maybe this document isn't relevant anymore, and we need to provide the user some way of like marking that and telling you that like, hey, here's an issue here, you should look at it. And I think a lot of software developers right now are not used to this like mindset of probabilistic, like, this is kind of like, we kind of got some upvotes on this, like, how do we go about handling this? But realistically, I'd say it's just like, start with like some feedback mechanism, add some like basic rules, and then that'll take you fairly far. And then you can get into, there's some really crazy things that you can do there. with just basically watching model drift and making sure that this stays good.
So Bard added a feature to kind of tell you the level of confidence that it had as for some things referenced. What are your thoughts around ways to represent how confident the model is to the user and kind of getting into that probabilistic space of saying this is a really rough guess, maybe this is what you want versus this is the document you want?
Yeah, so that's a fascinating idea. Really, really interesting. So what we do on our end currently is a much simpler version of that, where it's like we show you references and we show you what score it got in like an easy to digest manner, and maybe we could do some sort of ranking there to like figure out like as a whole how confident we are in queries. LLMs, this is kind of an issue with them where it's like a black box in the sense of like it's just always choosing the next most likely word, and it has a really hard time knowing that if it's confident in an answer. Like it just doesn't know it. Like picked the next chain of 100 words. And I'm curious, like what you're talking about, like almost sounds like maybe they have some sort of machine learning model to help with this. Something I'd love to look into, but as like a much simpler approach, literally just look at how good of a matches of embeddings were, and that'll give you a rough idea.
I know BBA does cosine similarity across the vectors.
Yeah.
To kind of give you something like that, but
Yeah,
I was wondering if there was anything better.
It's just like how you guys solve your problems, where the big question in RAG was how good the answer was, not how good the searches were. And so what they did is they just threw another LLM at it and said, here's the question, here's the answer. Now break this down 0 to 100 and tell me.
Interesting.
And that's how they worked around it.
Okay.
You had to try to gauge accuracy
Yeah.
of your answers, like in the QA loop. On the
Yeah.
backside one of these, that's what I came up with too. It's pretty good.
Okay. Yeah, I love that. And yeah, I've heard some variants of that before where it's like you use a second LLM to like check a word in the first one. It sounds like it's the same vein.
It's
Honestly,
LLMs
something
all the
we
way
need to
down.
Yeah. But really interesting idea. Anybody else? Go ahead.
I guess one question, when, prompt engineering and trying to get all these different target, the question he's talking about, so I kind of get the idea of like, okay, well, here's the query, go match a bunch of documents and put that into the prompt as context, right?
Yeah.
And then how do you decide how much of that prompt to use in context documents, or how much to put in it? Are you just, I know you might talk a little bit about filtering it out, but like, is there like a desired like length or summary compared to the question or
Yeah, so you recreate the results and like this is something that you can explicitly just ask LLM to do. Like maybe I want to limit it to 3 results or something. And that would be one way that Sheldon was mentioning is probably just another approach of, yeah, we can use an LLM as almost like the final step to just double check that we're going down the right path. So that would be one approach, but realistically you would, yeah, I think most of the time you're not going to get back that many responses that are relevant. It's not as well machine.
Yeah, I guess I was just thinking on prompt length, like how much, I guess, to, like if you're just throwing a lot of data at it and just saying, oh, it'll ignore anything that's not important, or does it cause like some biases or something in the answer, or maybe?
Yeah. So in our experience, the less you toss at it, the easier time it's going to have generating an answer. And it's just because like there's noise.
Mm-hmm.
Like the more stuff you add to it, there's more noise, and it might start doing weird things. So yeah, it's just something to watch out for. Like ideally, what you're feeding it is